So for a long time, the floods were actually dismissed by people who'd never even come out and looked at the landscapes.
Yeah.
Said, well, if you can't provide a source for the water, then the floods didn't happen. Basically, is what he said. My issue with it, and I've had some pretty extended discussions with various geologists that have been working on it, and it seems like that there's an Achilles heel in the whole theory, which is this ice dam theory. Because if you're talking about water 2,100 feet deep, you're looking at the heel of the ice dam at about 960 some psi. Now, glacial ice, especially temperate glacial ice, is usually riding on a layer of basal meltwater. It's riven with moulins and fractures and interstitial cavities, and it is not a good material for impounding water to any significant pressure. And what you actually see when you look at modern examples is typically modern examples of glacially impounded lakes usually fail between 1 and 300 feet in depth. And the idea of
we have one in Alaska that does that.
Yeah, there's self-dumping that will repeat.
Yeah.
So that's my issue with it. And I've also, traversed the region quite a bit, and there's a lot of field evidence that doesn't really seem consistent with a single outflow from the Clark Fork Valley. We did a traverse up the Okanagan up into British Columbia a number of years ago, and you can see evidence along that whole route from Lake Okanagan right on down to where it meets the Columbia of massive meltwater flows moving south through the Okanagan Valley.
If you fly over and you look down at these mounds, these big mounds.
The ripples, the current ripples.
The ripples.
Giant ripples, yeah.
Giant ripples that look like the bottom of a lake.
Yeah, except that they're huge. I mean, some of them are
They're huge.
30, 40, 50 feet in height and 200 to 500 feet in wavelength. So, yeah, those were actually created like at the waning stages of the floods. Yeah, did you fly over the ones in Montana, Camas Prairie, it's called? And then there's West Bar on the Columbia, which is a huge 3-mile bar. The flood gravels are 200 to 300 feet thick above the modern Columbia, and they're just mantled with those ripples. 2007, a team of scientists from Lawrence Livermore Laboratories and several others, geochemists, were looking at these Clovis sites around North America. The Clovis sites are dated to the same time as these floods, and there was considered to be the earliest culture that lived in North America. Well, some studies have suggested that the Clovis culture rapidly disappeared, and there would have been a hiatus about 1,000 years, followed by the Folsom culture. Well, this group of scientists was studying the remains of the Clovis culture, and they kept finding what they referred to as the black mat. And the black mat separated two geological events, one called the Balling-Alarod, which was at the end of the Ice Age. It started warming over 3,000 years roughly. Around 13,000 years ago, that slow warming was suddenly interrupted by a spasm of warming, maybe 15 degrees or more centigrade. Within the estimate now suggested it happened as much as within a year and a half. Okay.
Wow.
I believe that warming event was associated with the flood. Now, the first flood, and that was at 13,000 years ago. Now, over the next 1,400 years was a period called the Younger Dryas, where the climate shifted back rapidly into full glacial cold, and at 11,600 years ago, suddenly a second warming spasm occurred. And I believe at that point there was a second round of great floods, and that the floods are actually the melting of what is called the Cordilleran ice sheet over the Canadian Rockies. Because if you look in there, I mean, these mountain valleys were filled with ice up to sometimes a mile thick, and it's gone now. Where did that water go? And if you study the topography of the valleys, there was only one direction it could go, south. And when you follow those south, it leads right over the northern rim of the Columbia Basalt Plateau. So if you go east to where the lake was, the Lake Missoula, what you see is actually the Thompson River Valley and the Rocky Mountain Trench. Both head up into what would have been under the ice sheet, and they both empty into what was the basin of Lake Missoula. So in 2007, this team of scientists looking at this black mat analyzed its constituents, and they discovered that there was nanodiamonds and magnetic spherules and fullerenes. Yeah, what does that suggest?
That suggests like a meteor.
Yes.
Or an asteroid.
Yes. Yeah. And this has been a very controversial idea since then. Other teams came out and said, no, we looked and we didn't find it. Then they came back and looked again. They said, well, you were looking in the wrong place. In the last 2 years, I think the evidence has now shifted from dismissing it to going back to, because other independent teams have gone out and looked and have now confirmed that, a lot of this stuff, not at every site, but at many of the, actually preponderance of the sites show some of this signature of what was probably a cosmic event. And I asked the geologist down there during the lecture, what was the square miles of forest area destroyed in the blast here, and he said what was
270 maybe?
Yeah, something like that. And during the Tunguska meteorite blast in Siberia of 1908, there were 800 square miles of forest flattened. So 3 times the number of forest area as what happened with this blast. And that was, they're still arguing, was it an asteroid, a comet, or something in between?
Yeah.
And it was actually an aerial blast.
Right.
And there was a small iridium spike, just like at the Cretaceous Tertiary boundary of 65 million years ago that wiped out the dinosaurs. There was a big iridium spike. There was a small iridium spike at the Tunguska blast, and now this iridium is showing up at the black mat that separates the Clovis from the Folsom culture. So it's starting to look more and more like around 13,000 years ago, Earth got pelted big time.
Huh.
And see, I'm thinking that is where we need to look for the cause of the flooding.
Yeah.
And that the lake, rather than being a cause of the flood, was just another effect of the rapid melting over the Canadian Rockies. So, the water here rose up to roughly 1,200 feet above sea level. We're at 1150 standing right here.
Yeah.
And so that gives you a perspective, especially when you look out this way.
Yeah.
And you see how vast the body of water that they call Lake Lewis really was.
Yes.
In order to be this deep through the gap. And then, of course, all of that over there was submerged. All of this is your textbook channel scab land down here.
Right. So that was all submerged, and this also was submerged.
Yeah, but barely.
Yeah.
It just barely topped
Right.
this that we're on here now.
And it came from which direction?
Came from this
That way.
and then passed through down the. So this was the gathering of the waters here.
Right.
Here's where all of these great flood streams came together. Those twin sisters are a remnant of the. Basically, if you look, you can see look immediately to the left of the sisters. You see the shelf.
Right.
Immediately back,
Right.
you see a shelf.
Right.
That would have all been continuous.
Yeah.
You see, I believe, it makes sense, that was the pre-flood valley floor.
Okay.
All the way across.
Yeah.
And there would have been a lake on the upstream side,
Right.
but not anywhere near. It probably was a lake something on the size of what we're seeing here now.
Right. Right.
And this would have then been a sill or a spillway for the pre-flood Columbia.
Right.
When the floods hit, they ripped through here and just lowered the valley floor by about 200 feet.
Right. Right.
Based upon the present depth of the river and the height of the Twin Sisters.
Yeah. Yeah. Now the twins themselves, I mean, that's a basalt outcrop.
Yes.
But has that been sculpted by the flood, or is
Yes.
that? Yeah.
And had the flood continued for, let's say, another few days, a week, or whatever, they would not exist anymore. They would have been literally washed away.
Right. But they're quite deep underwater. They're 200 feet and 300 feet underwater.
Well, they're more like, they're about 300 feet above the floor, and we're at 1,200.
So they're 800 feet lower than us.
800 feet.
Yeah.
And really, if you look across, you'll see that uppermost outcrop of the salt, roughly on our level. And that would have been the high water mark. So all of this side of it, all of this down here was below water.
Yeah.
And that's what you're seeing there is that spectacular erosion of the salt. Of the water just dripping through here.
And what sort of speed?
Oh, through here, it could have been going 60, 70 miles an hour. Because the pressure, back pressure, has been so great.
Right.
It's been pushing it.
Right. Massive amount of pressure. Fearsome and ferocious flows.
Oh my God. Yeah. And so really, if you look out this way, the body of water was really like an inland sea, as far as we can see.
Yeah.
Except it's moving.
Yeah. Right. And it's turbulent.
It's turbulent.
And it's angry.
And the turbulence is increasing massively as it comes up to this constriction.
Yes.
But see, here's the thing. When you look at the capacity of this conduit here, of this valley, it would have had to have been a hell of a lot of water pouring in from the north to backflood to the extent that it did.
Right.
You see, the valley out of Lake Missoula is no bigger than this.
Right.
But it's 200 miles north of here. So how could that water have spilled out of there, traveled 200 miles to here, and not have attenuated to this degree that it would just pass through without ponding behind above the gap?
Right.
But it did.
Right.
Which to me is just incontrovertible evidence that there was more water pouring into this than what was pouring out of Lake Missoula.
Yeah. So we have 1,000 feet deep water, which turbulently flows through here.
Turbulently.
And then, how long does it stay that deep?
You know, the estimates are that it's probably 1 to 3 weeks.
Right. And then it starts to ebb away.
And then it starts to ebb away. Right. Because this, they call this hydraulic ponding. So this was a hydraulic dam through here.
Right.
Because the water itself
Becomes a dam.
becomes the dam.
Right, right. And there's been a comet impact, and we're expecting the sky is going to be bad too. There's going to be
Oh, it's got to be.
dark. There's a lot of stuff up there.
Stuff, and that's what I think is that 6-foot layer.
Yeah.
That's like frosting over all of the flood
Right.
sediments. You see this 6, 7, 8 foot thick layer of stuff called bus,
Yes.
which clearly had to come out of the atmosphere.
Yeah. It's like the Viracocha legend. He came at a time of darkness.
Yeah. Wasn't there something in there about the legends like a black rain or something?
It was, absolutely.
Yeah.
Like rain. That's it.
Yeah, I mean, these kinds of things to me suggest all of the myths and the stories. We need to look at those.
We need to look at them very seriously.
Seriously.
And see them as eyewitness testimony
See them, yes.
of events that occurred. Yeah.
Absolutely.
Cool.
Yep.
This is dramatic. Very dramatic. Well worth the drive.
Good, I'm glad.
And the gap, when we say the gap, that's it there, or that's the gap.
Yeah, this right
The whole
here
thing is
is the gap for about 3 or 4 miles.
Yeah.
It's a mile across right now. It's probably a little more than a mile from where we're standing over the Twin Sisters.
Right.
And it's probably the gap itself, I don't know, 3 to 5 miles through here.
Wallula Gap.
Wallula Gap. And then this is the Pasco Basin.
This also would have been the potential plug for all kinds of icebergs coming down and creating some of the layers like you saw in Burlingame Canyon, because that is up Walla Walla Valley there to the west or to the east that way.
Yeah,
Excuse
up
me.
in there is a valley that were those rhythmites, those rhythmical layers that we looked at this morning. What I'm seeing, once I've seen them here somewhere right down below us, are hundreds of erratics, iceberg rafted erratics. And all throughout the flood pathway are erratics that were carried by icebergs, all the way down into Eugene, Oregon, the south end of the Willamette Valley. You got a picture. We've got a moving scene choked with thousands of icebergs.
Wild scene.
Wild scene, and all of that is converging right here.
Yeah.
And over on the other side, we can't see. Well, we'll see that lake. That's, remember I showed you the big circular erosional features.
Right.
That clearly shows just how turbulent this stuff was coming through here. All of these icebergs are going to get jammed in here.
Right.
And what that's going to do is cause the water level to rise.
Yeah.
The pressure increases, pushes this down through the gap.
Yeah.
The water level drops until the next jam occurs.
Right.
And I think what we're seeing is a pulsating hydrograph.
Right.
That every time it rises, it backfloods further, up the valley.
Right.
And then the water level drops, and you see where those rhythmites are is close to the highest extent of the backflow.
Right.
So what you got out here is this, like I said, pulsating hydrograph.
We're on high land here. The human beings trying to flee remorseless.
Remorseless. And the thing is, even if you weren't on high enough ground,
Yeah.
the other conditions going on probably survive.
Yeah. Just be an awful.
Awful, awful.
So we're now looking north up the lower coulee,
We're looking north up the lower coulee,
and
and
what we see is so this deep cut in the ground that is the coulee was made by the floods.
yes,
Before the floods, there was just a continuous landscape here,
across there, yes. A
Yeah.
tilted landscape across from left to right.
and then this 60-mile-an-hour gushing
Came through,
turbulence
yes. Exploited
flow came through.
with the flexure of the rock.
Yeah.
It created zones of weakness,
Right.
fracture.
Okay.
The
so it
floodwaters
exploited the weaker zone.
exploited, yes.
Got you.
And those cliff faces there are about 900 feet high at the top.
Right.
And then you'll see there's a series of hanging valleys in between that was the pre-flood drainage topography. But now that's been completely disrupted. So now, I don't think too many of them are active, but you know, when you get a good rain, then there will be waterfalls coming out
I
each
see.
one of those.
I see. Yeah.
Each one of those. And you know, typically if you look up Hanging Valley, it'll show you pictures of glacially sculpted hanging valleys.
Yeah. Right.
But what this shows you here is that catastrophic floods can also create hanging valleys.
Right.
So there's beautiful.
So the flood, the main flood is rushing through the middle, scooping out everything underneath it.
Yes.
But there are waters coming down from the sides as well. Is that
I would think so, but not nearly like the flow that's being concentrated in the coulee itself.
right? The water coming out of the coulee at the head of the flood would have risen.
At
to
the peak
level.
of the flood would have been probably right at the level of the hanging valleys.
Right.
And initially, of course,
How high are they?
well, they're probably 600 to 700 feet because
Right.
the whole cliff face is about 900 feet high.
Yes.
You see how there are actually piles of gravel
Yes.
halfway up, 2/3 up. Again, that's, if you can picture a water flow,
Yeah.
if you've got a channel like this, a hydrologist refers to the wetted perimeter,
Right.
which is the total length of the contact zone between the water and the channel surface. That's the wetted perimeter. As the channel gets shallower, the ratio between the wetted perimeter and the channel width approaches 1.
Right.
You see, as the channel gets deeper,
Yeah.
like this, then the wetted perimeter gets much greater than the width.
Right.
So that kind of concept applies very much to the idea of the dam, the glacial dam, because in the glacial dam, where we will be passing through the Clark Fork Valley, the base of the channel of the valley is 5 miles. The height of it is at where the water level was 7 miles.
Right.
So the wetted perimeter is actually probably 9 or 10 miles.
Right.
So by implication then, you had to have 9 or 10 miles of perfect seal
Right.
between the ice and the substrate.
Right. Right. It's calling for a lot.
It's calling for a lot, yes.
Yeah.
And when we were at Mount St. Helens the first day, where I was talking about somebody and the lady that had a little bit of background, she says, well, I said, you know, it's just implausible that the glacier ice could retain water at that kind of pressure without leakage.
Yes.
And if there's any leakage,
It's going to undermine the dam.
it's going to undermine the dam. And she says, well, it was probably really, really cold. And I said, well, okay, let's surmise for a moment that it really, really was cold.
Yeah.
Then where did all the water come from?
Yes, exactly. There's a double bind there.
There's a double bind there. Yeah, you can't
It's
have
cold
it.
enough for the water not to undermine the dam.
Then
it
it's-
can't be water.
It can't be water anymore.
Yeah. I like that. Yeah.
And the water, there's only 2 sources for the water, rainfall or meltwater.
Yes.
And either one of those is incompatible with.
With the dam theory.
Because
When
now-
they envisage these ice dams, how thick do they think they are? So we've got one that's 9 miles long, you're saying, or 7 miles long.
Well, 7 miles across the valley,
Yeah.
and I can show you on the map. Here comes what's called the Purcell Trench.
Yeah.
Clark Fork River comes in at an angle like this. The theory is that the glacial ice, and I'm sure there was glacial ice, that came down the Purcell Trench, blocked off the flow of the Clark Fork River, and extended they estimate 25 to 30 miles south
Right.
of that intersection.
Right.
And then the water began to back up into the Clark Fork and backed up hundreds of miles into western Montana and
Right.
rose up to 2,100 feet deep against the dam. When my first trip out here, I went and interviewed a geologist who had done the most work on the site of where the dam was supposed to be.
Right.
I couldn't get him to commit to even telling me where exactly was the glacier water interface.
Right.
At the end of our 30-minute talk, he kind of in a way almost threw up his hands and said, well, he just didn't really even know about the ice dam.
Right.
Almost as if privately he's willing to admit that there's
Something wrong with the idea.
something wrong with the idea, yeah. And that was encouraging to me. That, because, you think of something and it's just, okay, this doesn't make sense to me, but, all of these geologists
They're saying that's what it is.
saying that's what it is.
Yeah.
Then you start talking to the geologists. We've been on multiple, geologist guided field trips out
Yeah.
here, and, as soon as you try to pin them down, then
Right.
they're not so sure.
Yeah. Because it's a very flawed theory. There's all sorts of weaknesses in it.
Yeah, and that's where there seems to now be this rivalry between the Canadian geologists and the American geologists.
Yeah.
Um,
Absolutely.
because the Canadian geologists are like John Shaw. He did a paper which I have with me in case
Yeah.
you'd like to read it. It's called Back to Brett's. I think it was John Shaw was the lead author. But basically it's arguing that there were other sources of water than Lake Missoula. Now he doesn't really attack the ice dam theory. He merely says there were other sources of water.
Right. Right.
But once you follow the implications of that idea, then it certainly does call into the question the idea of a glacially dammed lake.
Absolutely.
And then, of course, as we look back to the south, all of this is going to be deposits over here.
Yeah.
And if you were to dig down in it, it would be nothing but boulders.
All the way down for
Yeah.
a couple of hundred feet.
Yeah.
Okay. Great. Inside the lower coulee.
Lower Grand Coulee.
Lower Grand Coulee.
Well, we have a channel. Water's flowing through it.
Yeah.
Around the wetted perimeter, there's going to be the greatest friction. Right? Okay. So, and in the middle, basically the water is flowing with the least friction.
Right.
So it's flowing faster
Right.
as you move away,
faster in the middle.
faster as you move away from the wetted perimeter.
Okay.
Okay, so now, you know how a typical cataract has the horseshoe shape.
Yes.
Well, that's because the horseshoe is the inversion of the flow velocity. So in other words, here's a cross section. Let's say the water is flowing this way.
Yeah.
It's flowing faster in the middle,
Yeah.
and then it diminishes in volume as you move towards the edges of the flow. So what it does is it erodes faster in the middle
Yeah.
and slower towards the edges, and
Yeah.
that's what leaves the classic horseshoe profile.
Okay.
Also, now here we see we've got this like this.
Yeah.
So as the water begins to slow down, there's frictional energy losses against the side of the channel.
Yeah.
And so not only does it deposit on the bottom, it piles the sediment up along the flanks of the channel. see?
Right. Right.
So that's all this stuff you see here. All that is stuff that was trained within the water flow
Yeah.
at one point.
Yeah.
Then when the water began to decline down, it just left this stuff piled up against the flanks of the channel.
Right.
So it's not callus in the ordinary sense.
No.
Because callus will typically, as the callus accumulates, the cliff recedes.
Yes.
Because it's material falling off the cliff. This is not callus in that sense.
Yeah. So it's when you say it's not callous, you mean it's been dumped there?
It's been dumped there by the water.
Right.
It's been dumped there, washed in effect up on the sides by the water.
Right. And the sheer edge is because that has left that's one flow of igneous rock. which is
Basalt, yeah.
basalt, but that is stripped off the flow that was on top of it. Is that?
Yeah, the horizontal shelf
Yeah.
would have been one flow.
Yeah.
And it apparently was a fairly fluidized flow because it was able to self-level. Another flow comes in on top of it. Now you have a bedding plane,
Yes.
which is a zone of weakness.
Yes.
The friction of the moving water starts plucking this stuff, and it plucks it right on that bedding plane. So it is left. Now, had the flood continued beyond, well, you can see up there. You see what happens to the integrity of the shelf?
Yes.
It starts breaking up.
Yes.
And had the water continued flowing, then it would have gone to work on this.
Right.
So you got to realize there's the process, and then there's the end of the process. So as the flood waters, as the spigots are turned off, and the flood water dissipates, then it leaves it at whatever stage of erosion it was at.
Right.
So see, Grand Coulee was one of the great flows feeding down into Pasco Basin.
Yeah.
One of 5.
Right.
Moses Coulee was another one.
Yeah.
The Columbia west of here was another discharge conduit.
Yeah.
The Telford's Cadillac track to the east of here, and then the Cheney Palouse to the east of there, and then the Snake River was carrying huge volumes of water. And all of those were feeding into Pasco Basin. So that's Pasco Basin now fills up, and its only outlet is through Wallula Gap. So then as the waters rise, it's forcing the water under great pressure through Wallula Gap.
Yeah.
The turbulence was indicated by those great round pools we saw, and then everything from there had to go down to Columbia Gorge. The carrying material, and as it opened up into the Portland Basin, all that stuff dumped. So under Portland is 400 feet of probably, what is that, 20 by 20, probably several thousand square miles.
Down here.
Yeah. Several thousand square miles of material. It's going to be a finer material than we saw at the Ephrata fan, simply because it was carried farther.
Yeah.
But as we saw at the waterfalls, there was tremendous erosional work done all the way down from the gorge.
Right.
And we saw at Mozzarella Falls, again, the indication of the intense turbulence of the water in that undercut overhang the salt cliffs. Right.
So, Randall, the reason that it's here rather than somewhere else is because there was a fault line here or something. It was easier for the water to cut this than something else.
You'll see that the cliffs on the west are higher than the cliffs on the east.
Right.
The pre-flood topography, the dip, was from west to east. It was sloping down like this.
Yeah.
Because we're actually standing in a monocline.
Right.
And a monocline is a single fold upwards in the bedrock. So it folds up, and as it folds up, it cracks and fractures along that fold line.
Right.
So right there, that creates a zone of weakness.
Right.
And as soon as that water coming across, I showed you where the upper coulee is actually coming at an angle to the monocline.
Yeah.
As soon as it hits the monocline, it starts following the monocline.
Right.
Now, Brett saw, and when we get up there, it should make more sense to you, that when the water first hit the monocline, it formed a 900-foot, 5-mile wide waterfall.
Right.
And then that receded as it pours over the lip.
Yeah.
What it does is it pours, it plucks material. As it plucks, the cataract, the cliff of the cataract recedes. Yes, that's a receding cataract.
Yeah.
Grand Coulee, this whole thing here is a receding cataract form.
I see. Interesting point. Right.
Yeah.
It ate its way back.
Yes.
Yeah.
The source of this water, I think, is controversial.
Right.
It's assumed, I think, kind of implicitly, without actually getting into the details of it, that this came somehow from western Montana.
Yes.
But when you look at the configuration of the ice, I don't think so. I think it came north of here, out of Canada.
Right.
Again, I can show you the pictures better. The term supraglacial means flowing on the glacier, just a subglacial beneath, end glacial. in glacier as within glacier. I think this was supraglacial waters. I think the water's rushing over the top of it. There was actually two lobes that came together, the Okanagan lobe and the Columbian lobe. And where they met created sort of a trough that called interlobate. I think that served to channelize the supraglacial waters. And right at that point where the Okanagan lobe is like this, the Columbian lobe is like this, there's the head of Grand Coulee. You see? Feeding right into it, yes. Cool. So we're standing pretty much right at the edge of the monocline.
Right. So the land just sloped down a bit that way.
Yeah. Draw a line from the top of that cliff to the top of those cliffs.
And that's your monocline.
Yes, and that's your monocline.
And then
And the
waters came down through here.
through here.
And they cut it all out.
Yep. And just like scooped it and just sliced off those hills up there.
But you're saying that the cutting is more done by like a receding cataract. It's a constantly receding cataract,
Yes.
you think? Yeah.
Yeah.
So it actually, the cutting starts at the far end and it works its way back.
Works its way back.
Yeah.
Like Niagara Falls, they say, has migrated 7 or 8 miles
Right.
since the Ice Age.
Yeah.
Yeah, this happened in
Except this
weeks.
happens in the blink of an eye.
Right, yeah.
Because it's so powerful what's coming through.
Right.
You
Yeah.
can really see, I mean, that wash up debris.
Yes.
It's just so impressive to me.
Absolutely.
You got to just picture waves of this. You think a flood, really, we're almost looking more like at a slurry.
Yeah.
Almost like watery concrete more than we would be looking at water.
It's abrasive. It's quite
Abrasive, very abrasive.
Yeah.
And yesterday, standing on the rim of Wallula Gap, what we would have been seeing is literally just this massively turbulent sea of this stuff.
Yeah.
Laden with thousands of icebergs.
Right.
I mean, we're talking about, where we were standing, there would have been 1,000-foot waves washing over and through that gap.
Yes. Yeah. So how long's the flow lasting for?
The flow, probably a matter of weeks. Probably measured in weeks. I think days is too short, months is too long.
Yeah. But it's a testimony to the cutting power of that flow.
Yes.
And what it's carrying, which is part of the reason it cuts so much.
Yes.
We were just saying, like Niagara Falls has migrated 7 miles in 10,000 years. Here you have a migration of
much
more than that,
orders of magnitude greater
in a very short time. Because first of all, the volume of the flow is much greater.
Yes.
Secondly, it isn't just water. It's water and rocks and trees and icebergs.
It's sediment laden, very abrasive.
Sediment laden, abrasive stuff, which is heavy and massive and just
viscous.
Yeah. And it rolls and tumbles and cuts, and it's like a buzzsaw.
And what's moving through the estimates that I've seen are between 300 and 350 million cubic feet per second.
Wow.
So, if you took every creek, river, and stream on Earth, flowing all together,
right,
times 10 would be about the flow you through.
Seriously?
Yes.
It's that big?
It's that big. It's that big. This is 10 times the flow of every river on Earth flowing together. Every river.
My God.
From every continent flowing
Right.
And that's what's moving through here. 300 million cubic feet flowing here every second. That's a lot of water.
That's amazing.
A lot of water. And see, this is just, again, one of the flows.
Yes. Yeah.
And that's what I've been arguing, and that's what Shaw brought up, and that's what this Japanese team brought up, was that the capacity of Wallula Gap is great enough that one flow shouldn't have ponded above Wallula Gap.
Right.
In other words, there had to have been more water, just like our sink in our room was stopped up last night.
Yeah.
Right? It drained out slow.
Yeah.
If the water coming in is greater than the water going out, it fills up.
Yes. Yeah.
That's Pasco Basin
Right.
writ large.
Right.
So the capacity of Wallula Gap to convey the water out of Pasco Basin had to be less than the total volume coming in, or there would have been no rise of water at all. It would have just been a flow through.
Right.
And right there, to me, that's a major contradiction that just hasn't been addressed,
Right.
in my opinion.
Right.
I have not, and when we go up through the Spokane Valley, Victor Baker calculated that the flow through there was about 750 million cubic feet per second, which was about
double this.
Double this,
Yeah.
But Pardee calculated the flow out of Clark Fork at about 300 to 350, so roughly about the same volume as this. But then so picture, here's the Purcell Trench, the ice dam, Clark Fork.
Yeah.
Okay, 350 million coming through Clark Fork, double that below the ice dam. Major contradiction, and nobody's really addressed other than to say, well, Victor Baker's hydrological formula was more sophisticated than Pardee's.
Right.
But that more sophisticated hydrological formula over what Pardee used is not going to be a factor of 2 different.
No.
You might say, okay, we can get more accurate by 5 or 10%. He used what's called the Chesney formula. Pardee did, and then Baker used the step backwater method, which is much more elaborate. But again, you're not going to get the Chesney formula has been used by hydrological engineers for a century. And it's accurate enough for virtually all practical purposes. So I don't think that discrepancy has really been addressed. But I think the simple answer is that what Baker was measuring down here was including flows coming out of Canada.
Right.
That Pardee was not measuring.
I see. Yeah. Makes sense.
And when you go up into the Purcell Trench, there's evidence of southward flows.
Yeah.
Now the Purcell Trench is pretty flat, the gradient wise. So that means that even though it's a large volume, it's moving relatively slowly. If you've got, and see, this is what a lot of these trenches in the Rocky Mountains are relatively flat. But when they hit the basalt plateau, it does this.
Right.
So then you got this flow coming up here, and as soon as the gradient steepens, it speeds up.
Yes.
As soon as it speeds up, it becomes more erosive.
Right.
Because its erosion potential is a function of its velocity. So there.
Okay.
I have spoken.
You have spoken.
Let it be written.
Yes, let it be written.
You can quote me on that. Erosion potential is
Dry Falls.
Behind us is the falls. Right, look at it, a tremendous horseshoe. It's almost, more than that.
Actually, you can see there's an alcove, a horseshoe coming like this, which is a ridge separating this alcove from the next alcove over. And then beyond that, there's another alcove. And then way in the distance around the corner is yet another alcove.
So, how would you see the water coming over this?
Well, at the peak of the flood, okay, you got about from the top of the highest cliff edge to the base is about 400 feet.
Yeah.
The water itself was 400 to 500 feet deep as it came across. So at the peak of the flood, it wasn't even a waterfall, it was a bulge in the water.
This, in a way, is the. So this is the northern end of Lower Grand Canyon.
This is the northern end of Lower Grand Canyon. This is kind of what separates Lower from Upper Grand Canyon. And had the flood continued, this whole cliff would have just eaten its way to the north.
Way further back,
Yes.
So this marks the end of the
Yes, this marks the end of
way. It's eaten its way all the way back to here.
Yes. And you see how
during the course of it, there would have been stuff like this further down.
Further down.
Eaten away back.
Yes,
back.
you
all
got
the
it
way here.
exactly. Right.
Yeah.
Well, you can look at the vehicles down there.
Yeah.
Compared to the rubble over here, those are the size of houses just dropped.
Yeah. Very impressive.
You can see the boats down there. And so, roughly, these cliffs are about 3 times the height of Niagara.
Are they?
Niagara Horseshoe Falls would fit nicely right into that, right there. This rock out in front of us is called Umatilla Rock.
Right.
Had the flood continued for any length of time beyond what it did, that rock would have been washed away.
Right.
They call those rock glades.
Yes.
And there's a bunch of them. But that's a very prominent one, there's Umatilla. And you can see that the flood was eating its way through right there. And pretty soon would have probably created one alcove where there's 2 now.
Yeah.
And the far side of the complex is almost 5 miles.
Right.
This is giant. It's a giant thing.
It's a giant thing, yes.
I've never seen anything like this in my life before.
Very difficult to explain either Grand Coulee or Moses Coulee as a result of outburst flooding from Lake Missoula. And when you read through the literature, it becomes apparent that the exact process or mechanism is dealt with in a very vague fashion.
Right. Like they're just taking it for granted in a way.
Yeah.
Not really thinking it through.
Yeah. See, all of this stuff was being plucked off the walls. Yeah. And it's this stuff that when we visit the Ephrata-Radix fan, that's this stuff. It's been washed out at the lower end.
It's difficult to see how outburst floods come down. It's on the basis of the magnitude of the features. They're just
Yes.
too big. Yeah.
You know, and some of them are trying to explain Grand Coulee as being the result of some different flood,
Right.
older, but okay, so what's the source of that flood then?
Yeah.
Well, they say, well, it was a diversion of the Columbia. Really? Just the diversion of the Columbia did this?
Yeah.
Well, then, they're kind of implying, well, if it did something on this scale, you're looking at a very protracted erosional event over hundreds of thousands, if not millions of years.
Right.
And yet, clearly, this has all the characteristics of every other erosional coulee
That has happened.
that has happened.
Very quickly.
You've got hits.
Yeah.
And Brett's. Brett's didn't quite know how to fit Grand Coulee or Moses Coulee into the channeled scablands of Cheney Palouse or Telford.
Right.
But he still believed that they were cut by catastrophic floods.
Right.
And he wasn't sure if it was the same floods or different floods, and he doesn't really attempt to explain that in his pictures.
Yeah.
Here you see the monocline, and the monocline goes up like this, and Upper Grand Coulee comes in like this.
Right.
So it spilled over that 900-foot waterfall was right here.
Yeah.
And then it hit and spread out.
Right. Okay.
See, but then,
That 900 waterfall is off the edge of this.
yeah, it's like right here.
Yeah.
Like right here,
Yeah.
right there.
Okay. All right.
And it's coming across the Waterville Plateau off the ice sheet, which
Yeah.
is right here.
Yeah. So it's not simply coming down here. It's coming.
Yeah, it's coming at an angle. Here goes the monocline like this, and it's coming at an angle like this.
Right.
It hits the monocline, turns into a 900-foot waterfall, hits down, spreads out,
Right.
causes all this erosion. You can see there's multiple channels here.
Yeah.
But this was the weakest area because on that uplift, everything fractures in there.
Right.
So the water then exploited that and began to concentrate down this area.
Yeah.
And you can see, I mean, there's just like a labyrinthine complex of things. I mean, look
There
at all
is,
these
yes.
little cataracts.
Yeah.
They say little, they're not
They're
little.
big. Yeah. The whole thing is just a disaster area, basically.
The whole thing is just a disaster area. I mean, you couldn't even do this with hydrogen bombs.
Yeah. Massive destruction.
Massive destruction. And see, water actually sheet flooded over this area as well, and then you can see it kind of begin to concentrate down into here, and starting another channel right here, this Billy Clapp Lake.
Right.
And then flowed down here, and down here is Quincy Basin,
Yeah.
which we're not going to get to see. We're not going to get to see Potholes Cataract. But, yeah. I mean, even 2 weeks of every day out here.
We couldn't see it all. No, it's quite impossible.
Too big.
It's just way too much of it.
Yeah.
It's quite impossible.
Too big.
It's quite impossible. Just way too much of it. Way too much of it. Way too much of it. And massive destruction.
Massive destruction. Massive destruction. Massive destruction.
The whole thing is just a disaster area. Giant thing.
It's a giant thing.
I've never seen anything like this in my life before.
In front of Okotok Rock, Blackfoot word for big rock, and the conventional explanation here is that this was transported by glaciers, which it was in an indirect sense, but I maintain that glaciers, in transporting this rock several hundred miles from its source, would have essentially left very distinctive marks if they even preserved the rock intact to this distance from its origin. See, I think it's far more likely that this rock was transported aboard an iceberg, was what we would call an iceberg rafted erratic, of which we have looked at dozens and dozens, way too many to count, down in Washington State, Montana, and so forth, that is accepted by conventional geology as having been iceberg rafted. But one thing that indicates that this was iceberg rafted is the sharp edges on the rock that would have been ground off if they had been transported simply by glaciers, because glaciers move slow. And in the time that it took to transport this rock from its origin, it would have been deeply buried in the ice and likely pulverized, scratched, striated, ground up, and what you would not have had is all of these sharp, angular, pristine corners that you see here. Plus the rock, which we now see was broken into 3 places, it was fractured clearly at the time that it was deposited on the ice. At the same time, the separate pieces had to be transported intact, which again they wouldn't do being transported in a glacier itself. Much more likely that what you had was a major flood through here carrying icebergs, and on many of these icebergs was this metaquartzite rock that came from the Mount Robeson, Mount Edith Cavell area up near Jasper Park. And another thing that clearly to me makes the case for massive floods through here is that south of here, just this side of the border with Montana, there's a field of gigantic current ripples that is clearly an indication of major meltwater floods passing through here. Over to the east, we would have had the glacier front of the Great Laurentide ice sheet, and to the west, we would have had the Cordilleran ice sheet. At some point, those two ice sheets coalesced pretty much right where we're standing. And then as the glacier age began to ameliorate around 15,000 years ago, the ice sheets receded back and opened up this corridor through here. Well, it was this corridor that then served as a conduit for huge volumes of meltwater that would have come through maybe 12 to 13,000 years ago. And I would argue that that's when this erratic here was actually deposited, not the 30,000 years that they say on the sign, but 13,000. So what you have to have is a confluence of separate events. One, you have to have the landsliding onto the ice sheet, but then at the same time you have to have fracturing and melting of that ice sheet to create the huge armadas of icebergs that transported the erratic strain, of which this is the biggest, and to create the huge volumes of meltwater that could float those icebergs. You have to really do some mental visualization, because you have to picture, you know, most of these people will come out here and they'll see the big rock, but they won't picture in their minds that you've got this turbid inland sea choked with boulders and mud and just and thousands of icebergs hundreds of feet deep over our heads. It's just sweeping over this land, and two great ice sheets, one to the east and one to the west. You know that this was hundreds of feet deep because, for one thing, the iceberg to transport this thing was many times the size of this rock. And you know that icebergs are typically, 85% of the iceberg is below the water, right? So the water to transport the iceberg, of which this was cargo, had to be hundreds of feet deep. And that's also confirmed by the Milk River current ripples south of here near the Montana border. By the time glaciers would have transported this from the origin here,
it would have moved and rolled. There would have been scrapes and marks. And
it would have
had all these edges, like you said.
Yeah, it would have been buried under hundreds of feet of ice.
It would have never been. It would have been separated long ago.
And this was one piece before then.
Yeah, it was all one piece.
And so it did
probably when it got let down, it broke.
Freeze-thawed.
Stressed it, but probably in the ice.
You got a picture. You know what a nunatak is? It's where you've got, like, if you look over there in the mountains, and you picture that they're just buried in glacier ice, but all you've got is a few isolated peaks coming above. Those are the nunataks. So what you got to picture is that something caused like a major collapse out onto the ice sheet. That's then followed by fracturing of the ice sheet, melting, and then the transporting of these thousands of icebergs. You're going to have this huge iceberg sitting in this big rolling field of basically mud, what a geologist would call alluvium, which is going to be soft, right? Because it's sediment that's settled out of the floodwaters. Then the iceberg melts away, see? And this thing is essentially the final stage of the deposition of this thing is actually going to be a fairly gentle process. What started it is going to be inconceivably catastrophic, but the final stage of it is actually going to be a rather gentle process of that iceberg melting and setting this boulder down into the soft alluvium. And you can see how it's sunk into the ground. And at that time, the fractures would have opened up, and that's when the rocks would have split and become, in effect, separate boulders.
So there's other boulders, a little boulder over there. Are there some all around here? I mean,
yeah, there's hundreds of them.
Yeah.
Over a span of about 500 miles from the mouth of the Athabasca, where the Athabasca comes out of the mountains, all the way into Montana.
Yeah.
And right there near the border with Montana is a field of gigantic current ripples that really confirms the passage of huge volumes of water over this landscape. It's like the ghost event that hovers over this landscape that you don't see unless you've, trained yourself to see it.